So, as promised, here is some very brief discussion on AI for reducing emissions from power sector and manufacturing. As I said, each of these chapters has details on barriers, ways forward, and each one is not organized exactly the same way. So I'm going to just take the most salient points according to me and the summary, which is nicely provided at the end. Okay, so here is data and AI applications for power grid infrastructure. So power generation sources, optimized energy market operation and design, and demand side management and energy demand forecasting. This we are already doing, and there's a lot of demand for it, especially when you add renewables like solar and wind. They are not available all the time, so you want to manage intermittency, peak demand, and so on. So forecasting becomes very, very important in that sense. So let's see what main points there are here. So you have hydro, solar, wind, and geothermal, etc. Nicely, they have only given renewables, but of course you still have fossil fuel systems playing into it, and you have cable branch and power transmitters and transmission lines and data transferring towers, and you have distribution lines. Data store is stored in a server and databases here for the power grid control center. Okay, so power transformer is here and the cable bunch is here. Very schematic. So distribution lines then serving homes, commercial places, industries, etc. And you have data generated there as well as at homes. So this is the demand side management. So they all have solar rooftop solar panels as well, and so on and so forth. Okay, so you want to manage the demand side as well. And generation infrastructure, then a planning, operation and maintenance of generation infrastructure are complex tasks requiring attention to a variety of factors, including the size and expected lifespan of equipment, renewable resource availability, and transmission congestion. AI can play an important role in performing these tasks. AI can be especially valuable in siting large-scale renewable projects. Determining the optimal size and location of solar projects requires complex calculations which must consider weather patterns, grid constraints, and other factors. So there are papers reviewing these topics that you can follow up with, and they are looked at with different time scales, so short-term, less than 1 day, and long-term seasonal solar potential predictions, which can help optimize site-specific solar plant planning. But you also need decadal predictions because you want to see how climate change is going to change your solar potential as well. Similar complex planning challenges also exist for wind farm planning, which must consider terrain morphology, wind speed and direction, turbine type and costs. And there is a paper that applies AI models to study economic performance of wind farm design and wind farm wake interactions for planning decisions. And again, for wind also has a lot of infrastructure that goes with it even when it's offshore, and you want to be aware in 10 years whether winds will completely die down because you are investing lots of money in setting these up. So you have to be aware of your flexible design to deal with any change in the wind energy potential as well. AI for renewable predictions, then solar energy, so radiation and power systems for PVs, wind energy, wind speed, power prediction, production forecasting. You have marine and ocean energy, so significant wave height predictions, wave energy flux prediction. Hydropower, you will need reservoir level predictions, discharge forecasting, and management there, of course. Other sources of renewable energy like tidal, hydrogen, geothermal, and biomass also can be part of this renewable energy portfolio. Source-dependent inputs then going into randomized machine learning models, and essentially there is some randomness in the data altogether. The ML can then give you after it learns and gets trained some predictions to manage the energy system overall. So here are some schematics combining, cell phones, homes, transportation, manufacturing, etc., to manage the entire energy transmission. Battery storage is very critical for intermittency. Even with all the predictions, you always have uncertainties, and even with predictions, you want to be able to ramp up supply when solar disappears or reduces because of rain, clouds, whatever, or winds die down, and so on and so forth. And the charging network is going to be very critical as well. And there are already ideas I've posted under the course on drawdown, where we see how plugging in the EVs at night can actually put energy back on the grid and help short-term energy management as well. But you need to model them with AI and predict them as well based on behavioral data and so on. So, jumping ahead to summary, AI has significant potential to help decarbonize the power sector in several areas. So, short-term predictions based on time series data, which we discussed, and it's fairly straightforward when you actually have data, so you have predictors, predictants, and so on. Scenario development, such as for EV charging and renewable power deployment. As we said, we do want to plan these properly based on traffic patterns, highways, most used distance. If people are going from one city to another and there is 200 kilometers to cover, you can optimally place the charging stations, just like rest stops are in operation for a long time. Improving optimization, such as for planning problems. So many power grid optimization problems involve work with large nonlinear models, so AI can speed up the computations and provide optimization solutions that are impossible without AI, and so on. Systems integration, operation, and optimization. So grid infrastructure is becoming more and more inclusive and increasingly exposed to real-time uncertainties such as wind, solar fluctuations. So taking a systematic view instead of focusing on certain grid components is more critical than in the past. So AI has potential application in nearly all aspects of power sector management, including planning, monitoring, maintenance, and operations. AI is becoming an important tool to help decarbonize the power sector. However, AI tools for decarbonization are not yet widely deployed. Barriers must be overcome and risks addressed before that happens. So we'll get a sense of the barriers here because I skipped those sections. So summary, more than a third of the global carbon dioxide emissions come from the power sector, more than a third. So it depends on how you count it actually. AI is becoming an essential part of this sector due to the power grid's complexity and rapid growth in power sector data. AI can help with scenario development, short-term predictions based on time series data, and optimization problems and systems integration. AI has the potential to make decarbonization of the power sector cheaper, faster, and smoother. Opportunities abound in generation infrastructure, transmission and distribution networks, end-use sectors, and energy storage. Examples include determining the optimal size and location of solar and wind power projects, predicting weather relevant to solar and wind generation, improving fault detection, outage forecasting, and stability assessments on distribution grids, and facilitating deployment of demand response and vehicle-to-grid programs. Several barriers limit adoption of AI for decarbonizing the power sector. AI models and methods are not yet sufficiently robust or well developed for widespread deployment. Standards for performance evaluation are lacking, and knowledgeable workers are in short supply. Security risks must be studied and properly addressed before deploying AI for most grid infrastructure. So they are always exposed to cybersecurity issues, hacking, and disruptions, and of course unintended consequences as well of climate hazards and so on. Okay, so here are some examples of factory operations. Factories are increasingly digitalizing their operations. Factories comprise thousands of interconnected sensors, and Automation, electrification are always critical and reduce human errors, but they come with a lot of implications in terms of barriers, uh, you know, error-prone systems, and so on. So here is for manufacturing plant plus over design safety factor. So virgin feedstock, recycled feedstock, and reliable products plus waste and excess CO2 equivalent, so non-CO2 greenhouse gases included. Uh, Mostly only recycled feedstock for a manufacturing plant with all optimization, so reliable products with net CO2 equivalent reduction. This is just a schematic of how AI can enable manufacturers to adapt to recycled feedstock. Factories typically address the increased variability of recycled feedstock by planning for the worst case scenario. This leads to unnecessary waste and excess emissions. Instead, factories can use AI to optimize operations and produce equally reliable product with net CO2 equivalent reductions. Okay, so here is a case study of alloy additive reduction in steel making. Steel and cement and aluminum remain highly uh, undesirable contributors to global warming, but they are essential for all the things humanity wants to do, especially developing economies like China and India, building all the infrastructures and buildings. In 2022, a Brazilian steel manufacturer using AI achieved 8% reduction in alloy additive consumption. This reduction came with a commensurate $3 per metric ton cost savings and a 7.5% reduction in CO2 equivalent per metric ton of the materials used, feedstock. This company achieved these results by acquiring recycled scrap metal for their production, measuring the chemical composition of each batch of scrap, leveraging AI recommendations during melting to add as little, if any, additives as possible, predicting the risk of producing each batch of steel, trading off potential quality issues with emissions, and reducing the quality of variation of their final product. So adopting AI as part of plant's operating workflow, manufacturers can progressively target high opportunity use cases within their production. The adoption of AI in manufacturing also comes with a variety of risks. So need for regular maintenance, which is anyway necessary, but AI adds additional checks needed for making sure that the operations don't go bonkers, because AI is deciding a lot of things on its own by monitoring various components, as we saw here, right? So then you need additional and new safety procedures to deal with AI integration. So AI-based systems must be validated to perform as expected under normal and abnormal operating conditions. Any personnel working with AI systems may require additional training. These are job opportunities, but upskilling is very necessary so people don't lose jobs, and then you have other unintended consequences in political choices during elections and so on. Application of AI to maintain or increase emissions. As a general purpose technology, we have no way of stopping bad manufacturing actors from applying AI toward use cases that either maintain or increase their carbon footprint. So they may be increasing production and profits without worrying about carbon footprint. Regulatory pressure and market dynamics, along with other incentivization, are ways to minimize this risk of moral hazard of using AI to increase profits but not reducing emissions. So what is the summary of the chapter? The manufacturing sector accounts for roughly 1/3 of global greenhouse gas emissions. AI has significant potential to help decarbonize manufacturing by optimizing existing industrial processes and operations in cost-effective ways. For example, AI can play an important role in steel making with electric arc furnaces, an important decarbonization technology in which steel is made with recycled scrap metal instead of coal. AI can help address the variability in each batch of scrap metal, recommending optimal production settings to adapt to the variability. Using AI tools, one Brazilian steel manufacturer achieved an 8% reduction in alloy additive consumption using AI, cutting both costs and emissions, as we just saw with the blurb. More broadly, AI can help decarbonize manufacturing by enabling manufacturers to adapt to production issues faster and better, avoid past mistakes by leveraging historical data, improve production yields, promote recycling and circularity by adapting to variable recycled feedstocks, minimize energy consumption, adopt alternative energy sources, and optimize manufacturing schedules and supply chains to reduce logistical overhead. Circularity, of course, is basically where you have end-to-end dealing of a particular process like manufacturing steel, where you go from uh, mining of ores to the processing them, feedstock production, what happens after use, and so on. So it's called circularity or circular economy, which is discussed elsewhere as well. Okay, so next up is cement, and because I'm already here at about 16 minutes, maybe we can read this off as well. uh, yeah, let's leave it. It's actually innovation of materials, and we'll do it in the next podcast. Okay.